Hey, y'all, today we're going to move on to our next unit, and we're going to start in Chapter 17 talking about sampling distribution models. So I'm going to start out with an example. Gallup took a poll of 1,007 people and asked them whether or not they believe in the theory of evolution to be true. And so this is sort of a yes/no answer, and they found that 43% of those 1,007 people responded yes, that they believe the theory of evolution to be true. And so the question is, does that mean that's the actual proportion of people who believe in the theory of evolution? And if we took another sample of the same size, would we get exactly 43% of the people to say yes? The answer to that question is probably no. Um, because there's variability, sometimes we might get more people to say yes in a sample, and sometimes we might get less. And so what we have here is, I did not do this. This is from the book. They took samples size 1007, and a simulation was run to see how many people would say yes based on that 43% value that Gallup had found. And then they ran that simulation 2,000 times. And so this histogram here is a histogram of the proportion of people who said yes, they believe in evolution, those 2,000 times. So we don't have a distribution of one sample. What we have a distribution of is the proportion who said yes from 2,000 samples. We have a distribution of sample proportions, which is different than something we've talked about in the past. So again, we simulated 2,000 times, asking 1,007 people if they believe in evolution, and we took all those proportions and put them in a histogram, and this is what we came up with. You should notice, it's been a while, you should notice that this is approximately unimodal and symmetric, and that should spring to mind a normal model. And so what's actually been shown to be true is that a normal distribution can approximate a sampling distribution of sample proportions. So if we keep sampling and we sample always the same sample size, if we were to sample every possible combination of 1,007 people and ask them if they believe in the theory of evolution, which that would be impossible, but if we did, and we plotted all of those proportions in a histogram, it would be approximately normal. And so here we have 2,000 of those done, and it looks pretty normal here. Obviously, the tails are a little bit off. It's not perfect, and that's why we say it's approximately normal. And so this is going to help us because we can get samples and find a proportion of people in a sample, and then we can use a normal model to sort of figure out how unusual is our sample, or how far away from the mean is it. And so here are some ways to make some calculations. The mean for our sample, so remember the difference between p hat and p. P represents a population proportion. P hat is something that we got from a sample. Here we can calculate the standard deviation for our population proportion. Remember again, Q is 1 minus P, and that's the way it'll show up on the formula sheet. And so what we end up with is a normal model with P as its mean, the population proportion, and this square root of PQ over N as its standard deviation. And this is just a bit of notation like we talked about in class. A normal model with mean P, standard deviation, PQ over N square rooted. So this is going to make way more sense if we do an example. Of course, before we do that, we're going to have some conditions. In order to say that a normal model fits, we have to meet some conditions. In our samples, we have to have independent samples. So the individuals being sampled need to be independent of each other. of course. We also need to have a random sample taken. We can't just we can't have bias in our sample. We want to sample less than 10% or less of the population. And then we need to make sure our sample size is large enough. And the way we do that is we make these two calculations. We multiply n, the number of people sampled, by p, the proportion, population proportion. Same thing with n times q. And both of those need to be bigger than or equal to 10. So what's that saying is our sample size is large enough if we can expect at least 10 successes and at least 10 failures. So in our example we started with at least 10 people who would say yes, they believe in evolution, and at least 10 people who would say no. So take a second, read this. This is from the book, page 450. So we're doing a study of BMIs of college women or college students. I believe they say women, yep. And we want to know if the proportion they got of 31 students out of 200 is unusually small. Now remember, when we talk about unusual, we should be thinking about greater than 2 standard deviations or less than 2 standard deviations away from a mean. And so if we want to use a normal model to help us out here, we need to make sure we meet our conditions. All of these students are independent of each other. They told us they took a randomly selected sample of 200 female students. And this 200 female students would definitely be less than 10% of the entire population of 18-year-old women in the United States. We're also going to check that our sample size is large enough, so we take our 200, multiply it by what they report as the percentage who have a BMI of 25 or more, 22%. Do the same thing, 200 times 1 minus p, or q. And so we could expect from the sample of 200 to get 44 successes and 156 failures. And so we're good. Our sample's large enough according to that rule. So what we want to do, since we know that unusually small results are results that are 2 standard deviations below the mean, we want to figure out what is the mean and standard deviation. And then we can find a z-score to see how far away our actual proportion of 31 students out of 200 is away from that mean. So our mean is what the CDC has reported to us. Our 22% of 18-year-old women have a BMI of 25 or higher. We're going to use that 22% and 1 minus 22% to calculate a standard deviation for our sample. So 200 is our sample size. 22% comes from the CDC. 78% is 1 minus that 22. And so we get a standard deviation of 0.029. So because we've met our conditions, we can use a normal model with a mean of 0.22 and a standard deviation of 0.029 to decide if the results here are unusual. We had 31 of these 200 randomly selected females who reported a BMI of 25 or higher. And so from our sample, we have a proportion of 0.155. Different from the CDC, but is it unusual? That's what we're trying to figure out. So we find a z-score. It's been a while since we've done that. Remember, we take the sample and subtract the mean. So in this case, our sample proportion minus the population proportion, and then divide by the standard deviation. It looks like this, and we get a z-score of minus 2.24. That means that 31 over 200, the proportion we got from our one sample, is more than 2 standard deviations below what the CDC is reporting as the actual population percentage. And so that is unusual. We're less than 2 or were more than 2 standard deviations below the mean. And so we would say that the proportion of high BMI students is unusually small in this sample of 200 students. Here's another example from the book from 451. Take a second to read it here, or you can read it in your book, and then we'll talk about it. So here we're told that 13% of the population is left-handed, and then we have this auditorium with 200 seats in it, and it's been built with 15 lefty seats. So we have 15 out of 200 seats that are lefties. And so we want to know that if we bring in a class of 90 students, what is our probability that we'll not have enough seats for the left-handed students? So we have proportions here. We're probably going to use a normal model to see the percentage or the probability that we won't have enough seats. And so we need to check conditions. Our sample of 90 students, these students are going to be independent of each other. One person's not a lefty because the other one is. Classes are usually randomly put together, so this collection of 90 students is random. It's less than 10% of the population. If we check our NP, NQ, using that 13% that's reported to us, and then 1 minus 0.13. And so we should expect 11.7 lefties and 78.3 non-lefties, and so those are both bigger than 10, and we're good to go. So again, just like the last one, we'll find our mean and standard deviation. The mean of our population, or our proportion, is 0.13. Sorry, I'm having a little tough time with the color. And we can calculate our standard deviation using this formula and get 0.035. The next thing we'll want to do, we'll get our actual sample proportion. 15 seats are lefties. We're looking to see if we'll have 15 lefties out of 90 because there's 15 seats in the auditorium. And then we're going to calculate a z-score. All right, y'all. Well, I seem to be having a problem with Smart Notebook, so we can go through this problem together in class. You've gotten some of the basic information. This is a difficult topic, so if it's a little fuzzy or a lot fuzzy, that's okay. We're going to do a whole lot of these together. Again, I'll go over this in class. I'm sorry for the interruption in your learning.